Alright, so now let's start our first video of 2 on graphing. So how do we graph functions? Well, let's talk about some things that we need if we want to graph a function well. And in our first video, we're going to talk about how to draw a graph of a function we're very familiar with and make sure we put all the details on properly and what those details are. And then in the next video, we'll do a slightly more complicated example where we graph something that's genuinely unfamiliar with us and we have to figure it out. But what do we need? If you want to graph something, what do you need? Well, there's some basic information that you need. You probably want the zeros of the function, if possible. If a function goes through the x-axis, you probably want to know where. That's fairly important information to indicate on the graph. We need some values. So oftentimes, I'm going to put in a whole bunch of other details, but at the end of the day, just to sort of get a bit of a foothold, if you want to start graphing something and you want the graph to look reasonable, you might want to plug in a couple of points, figure out some values you understand, maybe plug in 0, plug in 1, that sort of thing, to help you graph the function. The more detailed things are, you want to know where the function is increasing versus decreasing. So for that, you're going to have to compute its first derivative and figure out when that first derivative is positive or negative. You are most likely, well, you're definitely going to want to know where the local and global, if applicable, maximum and minima are of the function. All right, so you're definitely going to use everything we talked about before in terms of finding extrema. You're going to want to indicate those on your graph to have a good graph. We're also going to want concavity and inflection. To make the graph look right, we mentioned this before, we want to know when it's concave up and concave down and at what points does the concavity change. So of course that has to do with finding the second derivative. So then, one thing, and this isn't going to come up with the first example, but that's going to be end behaviors and asymptotes. Yes, so basically if you have a function that has some vertical asymptotes, some horizontal asymptotes, you're definitely going to need to include those on your graph. That's very important information about the function. It really helps you visualize it. And also, if what I mean by end behaviors is if you have like f at x is equal to x squared. It goes up and up and up to infinity as you go it on both ends. Some functions go maybe up to infinity on one end, down to 0 on the other, etc., etc. So you need to consider end behaviors and asymptotes as well. So let's start with an example that again is familiar to us, which is f at x is equal to x cubed minus 9x. So yes, we know what the graph is going to look like. Yes, we've seen it many times. Yes, I can sort of draw it in my head, but why does it look like that? So let's find everything. So let's just go through this list. So the zeros, they're going to occur at x is equal to 0, minus 3, and 3, just by factoring this polynomial here. We care about some values, but generally we want to worry about those at the end. Once we have all the other information, we might say, okay, I think I can draw the graph just from this information, but sometimes it's still a little difficult to see, so I would generally sort of see if we need to find some values. I would leave that till the end. So let's talk about when this function is increasing versus decreasing. So here, what do we have? We compute, as we've done before, f prime x is equal to 3x squared minus 9, which is 3 times x minus root 3, x plus root 3. So we have that the function is increasing for x is less than minus root 3 and x is greater than root 3, and we have that we're decreasing between these two values. For minus root 3 is less than x is less than root 3. So how did I figure that out? Well, I know that this function here is a parabola, and it's an upward-facing parabola because the coefficient in front of x squared is positive, and I know that it has two zeros at root 3 and minus root 3. So this parabola has to be positive at values less than the left-hand root, positive at values greater than the right-hand root, and negative in the middle, which is exactly what I've written down here. But now we can also see from this information, so what's sort of nice about this is we get dual duty. From this information, we can now see that we can use this first derivative test to show that we have to have a maximum at x is equal to minus root 3 and a minimum at x is equal to root 3. Why? Because around negative root 3, the derivative starts out positive and then is negative afterwards. That means that you have a maximum. And around root 3, the derivative starts out negative, then moves to positive, which means that you have to have a minimum there. So you have to do this all anyway. So luckily, in this case of graphing, the first derivative test sort of comes for free because part of the graphing process involves figuring out when the first derivative is positive and negative. So finally, for the concavity, we have that the second derivative is equal to 6x. So this means that we're concave down for x is less than 0, concave up for x is greater than 0, and we have an inflection point at x is equal to 0. All right, so how can we put all of this information together to draw a graph? Finally, in terms of end behaviors, because this is a cubic polynomial, we know that it goes up to infinity on the right and down to negative infinity on the left, so that should now be enough to draw it. I guess let's try to graph it right here. So what do we have? Well, let's just indicate the points that we care about. We know that the function has a 0 here at 0, it has a 0 here at 3, and it has a 0 here at minus 3. Okay, and we know that, let's add in these 2 points, root 3 and minus root 3. So what do we have? We know that we have a maximum here, all right, and we know that we have a maximum here. The function is increasing here, decreasing here, and we're concave down here. So the function has to look something like this here, because we have a maximum here and we're concave down, so this does everything we want. It illustrates what the derivative looks like, what the concavity looks like, and gives us a maximum here. Similarly, we have a minimum here and we're concave up. We're decreasing down to here and increasing up to here, which means the picture here is going to look something like this. Also, just in how we've drawn it, we have this point of inflection because we have that the concavity changes here. Now, from minus 3 onward, we have that the function is increasing here, and it just keeps going down, down, down. It's concave down in this region, so the graph just has to look something like this, and it has to continue on something like this. And indeed, what you might want to do, and what your teacher might ask you to do, is you might be asked to, for example, indicate on this graph all of this information. You might want to draw it on here. But nonetheless, this is how we graph something like this, and this is all the information we put into it, and that's how we take this information and turn it into a graph.